All right, well, good afternoon, everybody. It is Wednesday, May 21st in the afternoon, and we are going to go ahead and get started with some new material. I'm actually going to start you off from the very beginning, from the review section, and we're going to do a quick review of some material that you should already know prior to have started in this class, but I'm not going to assume that everyone is expert, even though there are prerequisites for this class. So let me go ahead and get my pen set up here. And here we go. So we're going to review the set of real numbers by going through and looking at some basic ideas with numbers. And the first idea is is that of a set. A set is the most basic building block that we use in mathematics. And a set is nothing more than just a collection of things. Could be fruit, could be people, or it could be numbers. And we typically indicate a set by using a set of curly braces, both a closing and an opening. So there's an opening curly brace and a closing curly brace. And within the set of curly braces, we can explicitly list all of the numbers in our set. So here we're saying that set D consists of the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We could also specify a set by saying that the items have to satisfy some sort of property, in which case we can use this sort of set builder notation. So for example, here we say that D is the set of X such that X is a digit. And of course 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are digits. So these two sets are really the same thing, just two different ways of expressing them. So here we have set builder notation. And up here we have more of an explicit listing. All right, you can use set builder notation for an interval, for example, like this. So if you want to talk about the set of real numbers whose absolute value is less than square root of 2, then you can write it like that. Besides, there's an infinite number of numbers that satisfy that requirement, and we wouldn't possibly be able to list all of those numbers, but here we can at least tell you what the set is by describing the property. And by the way, this vertical bar right here means such that. In other books or situations, instead of a vertical bar, you might see a colon. Moving along here, so here's another example. We can say, the set of even digits can be written like that using the set builder notation or the explicit listing. Another word for the explicit listing is the roster, as in the roster method. Roster as in you're explicitly listing them, just like you would see on a roster. Here we have the set of odd digits. Now that you have remembered what sets are, now we can talk about doing operations with sets. One of the first things that we could talk about here is taking the intersection of two sets. So we have set A and set B, and the intersection is indicated by that upside down U. And when you take the intersection of two sets, that creates a new set whose elements are both in A and B. Just like, when you look at two streets that intersect, well, then this part right here is the intersection. It's the real estate that is shared by both of the streets. You could also take the union of two sets, A and B, for example, and here's the notation with that upward capital U, except it's not a U, it's sometimes called a cup. But this says that, when you take the union of two sets, it creates a new set whose elements belong in either A or B, or possibly both. So let's look at an example. Let me get rid of this ink here. So suppose that we have this set A consisting of the numbers 1, 3, 5, and 8, and the set B consisting of the numbers 3, 5, and 7. And let's bring in a third set consisting of 2, 4, 6, and 8. Let's take a look at what A intersect B is as our first example. Now A intersect B will be the set of numbers that are both in A and in B. And you can see that 3 is in there as well as 5. 3 and 5 are numbers that are both in A and B. So here is our intersection. Let's take a look at the union there for part B, the A union B. Well, here's A, here's B, and the union will consist of the set of numbers that are either in A or in B or possibly both. Now, one way that you could proceed is to go ahead and write all of A, 1, 3, 5, and 8, and then take a look at B and see what's in B that's not already listed. In this case, 3 and 5 are already listed, but 7 wasn't, so we could put 7 in there. You don't necessarily have to write the numbers in the set in ascending order, but it's useful. All right, let's take a look at the third problem here. We're being asked to find the intersection of B with the union of A and C. So what you need to do is to do what's in the parentheses first. Let's take A union C. So here, over here is A union C. And A union C is this set right here. And then you take the intersection of that with B. And of course, you'll end up with the 3, because 3's here and here. And 5, which is here and here. Okay, so that's how you do the intersection of a union. Do the union first, as indicated by the parentheses. Now, if there were no parentheses, then I would just say go from left to right. Do the intersection first and then the union. But if you do have parentheses, then do what's in the parentheses first. All right, so we've talked about unions and intersections of two sets. You can even do an operation on the single set. That operation is called complement of a set. And no, we're not saying nice things about the set. That's not what it means. What the complement of a set is the elements of the universal set that are not in the set that you're taking the complement of. And I'll show you an example here in a minute. But the notation that's typically used is the overbar of that set that you're taking the complement of. So right here, that's the complement of A. Sometimes you'll see this notation with an asterisk. Sometimes you'll see a little tick mark instead. All mean the same thing, that you're taking the complement of a set. Okay. So for example, suppose that we've got this universal set think about this universal set as the backdrop. All other sets are going to be subsets of this universal set. And suppose that we have this set A right here, and if you wanted to find a complement, then you'll list all the elements of the universal set that are not in set A. So what you could do, one handy way of doing this, is to go through the universal set and strike out the elements of set A, 1, 3, 5, 7, and 9. And then you're left with 2, 4, 6, and 8. And indeed, there's your complement. Okay? Now, the Venn diagram is a handy way of sorting out logical arguments and helping us also identify unions and intersections and complements and so forth. The universal set is indicated by this rectangle. So we understand that the universal set is contained within the rectangle. And each circle within the rectangle represents a set. So set A, for example, right here, all of set A is indicated by the circle that A is within. And here's set B and set C. And when you see two circles intersecting, like for example A and B, then that is going to be the intersection of A and B, for example. Or if you see this common point, that, well, it's the real estate that's common to both A, B, and also C, well, then that's kind of a super intersection, like that. It's the intersection of A, B, and C. Moving along here. Now, here's one possible relationship between sets A and B. You could have set A that is completely within set B. So A could be a smaller set relative to B, and everything that's in set A is also in B. But B would have some elements that are not in A. So, for example, B could be the set of animals, and A could be the set of mammals. Now, every mammal is an animal, but not all animals are mammals, for example. But here is the notation for subset. We say that A is a subset of B, and with this little horizontal bar down here, that indicates the possibility that A and B actually could be the same set. But that's kind of like saying that in real numbers that 3 is less than 3. 3 is less than or equal to 3. Leaving open the possibility that 3 and 3 are the same number, which of course they are. Now, it could be that we have two sets that do not intersect. They have nothing in common. Another way of saying is that their intersection is empty. What they have in common is nothing. When you see this symbol right here, this big fat O with a slash through it, we call that the null set, or otherwise known as the empty set. And when A and B have nothing in common, their intersection is the empty set, we say that the two sets are that they are disjoint. A and B are disjoint. They have nothing in common. Now, it could be that A and B do have something in common, and that they do intersect, and there's the intersection right there. When we take the union of two sets, we're talking about the new set of items or elements in the universal set that belong to either A or B or possibly both. And you could see that both circles are shaded. Here's what the complement looks like. We have set A, and then complement A is everything that's in the universal set that's not an A. Okay. Moving along here. Now we're going to talk about classifying numbers. We have a big old universe of numbers, and we should remember what each of the individual sets of numbers are. Now, we can actually start off with natural numbers. Now, the natural numbers are talking about 1, 2, 3, ... It's the counting numbers. Okay. Now, the whole numbers are going to be the natural numbers together with 0. The integers are going to be all the whole numbers plus the negative natural numbers. So any negative or positive whole number. And also 0 is the set of integers. The rational numbers are the numbers that could be expressed as the quotient of two integers. Quotient, that means division, right? So if you could write your number in this form, one number over another number as a fraction, then you have a rational number. And by the way, not only do we have numbers like 2/3 and 5/6 and -7/13 or whatever, but also any integer could be written as a ratio or quotient of that integer with 1. So, for example, 3 could be written as 3/1. So any integer is also a rational number. As we can see down here, rational numbers may be represented as decimals. But these decimals are either terminating or repeating. Like you see here, they have repeating groups. So they're either repeating or they terminate. Something important to remember, that rational numbers, when you look at their decimal expansions, those decimals either terminate, like you see here, or they repeat. All right, so that's important to know. That's why I repeated it. And then finally, we get to irrational numbers, which are real numbers that are not rational. And we're talking about pi, square root of 2, cube root of 11. So lots of different roots. Pi, e, which we'll encounter later in the course. Phi. There's lots and lots of irrational numbers. In fact, it turns out that even though there's an infinite number of rational numbers, the sort of infinitude for the number of irrational numbers is actually at a higher level. Yes, there are different types of infinity when it comes to counting. So, and the thing about these irrational numbers is that they cannot be expressed as a fraction. So if you were to take a look at their decimal expansion, the decimal neither repeats nor terminates. So, for example, if you were to plug in pi in your calculator, 3.14159 ... there's no groups of numbers that repeat themselves. and certainly doesn't terminate. That's the same thing. That's the same truth for any other irrational number. So here we got square root of 2, which could be thought of as the length of the hypotenuse for this right triangle here, or pi, which is for any circle the ratio of the circumference to the diameter. So square root of 2 and pi are examples of irrational numbers. So if you wanted to create some sort of Venn diagrams for the set of real numbers, well, we could break it down starting off with our natural numbers here in the green, and then we move up to the whole numbers and then the integers. Now, as we go from the inside, from the green outward, we're going up into bigger and bigger sets. Every natural / counting number is also a whole number, but a whole number consists of all the natural numbers together with 0. So that's why the natural numbers form a proper subset of the whole numbers. And of course, the integers have the negative whole numbers together with the positive, or at least the non-negative whole numbers. So -2, for example, is a number that's an integer that is not a whole number. So that's why the integers form a bigger set, and the whole numbers form a proper subset of the integers. And the integers form a subset of the rational numbers. And over here we've got the irrational numbers. There are not any numbers that are both rational, irrational. So the rational, irrational are disjoint from each other. And the rational together with the irrational numbers make up the set of real numbers. So if you have a real number, it's either going to be irrational or rational. There's no other choice. Okay? Moving along here, so here's a quick exercise. Look at this set of numbers and see if you could pick out the natural numbers, the integers, the rational numbers, irrationals, and the real numbers. Now, starting off with the natural numbers, 10 is the only natural number. Remember, natural numbers are basically positive integers. And then the next one, part B, is the integers. The integers are going to be the whole numbers that are, positive or negative whole numbers together with 0. So that includes the 10 and the -3. And then part C, the rational numbers. Rational numbers are going to include all the integers together with fractions or numbers that are decimals, where the decimals either terminate, like 0.12, or they're repeating, like this number here. And then for part D, the square root of 2 and pi are irrational numbers, per our previous discussion. The real numbers are going to be all of these. All of these numbers are real numbers. Now, when we talk about expressing a number, if you have a decimal with several places, you may only be interested in the first 2 or 3, and then you want to somehow chop it off. Now, you could either truncate it, which means that you actually are going to chop off all the decimal digits after so many places. Otherwise, we would round. And we're talking about the normal rules for rounding. You look to the right of the desired place that you're rounding to. And if that number is 5 or higher, then you'll round up. If it's 4 or less, then you'll keep it as it is. Okay? So, for example, suppose that we got 20.98752, and we want to truncate it to 2 decimal places. Then what we do, so there's the second decimal place at the 8. Then we look to the right. Now when you truncate it, you just chop everything off to the right, and you'll write 20.98. Okay, regardless of what digit is to the right of 8. But when you round, notice that number to the right of 8 is 7, which is 5 or greater. So that means that you'll bump that 8 up to 9. So now you'll have the rounding to 20.99. Okay, for example. Here's another quick example. I'll let you look at that real quick if you need to do some truncating versus rounding. 3.14159, round it to 2 decimal places. Now here's the 4, right? 2 decimal places. Look to the right, that's a 1, that's less than 5. So you'll just round it to 3.14. Or if you want to round it to 4 decimal places, well, the 5 is at the 4th decimal place. You look to the right, that's a 9. This digit right here is a 9, that's greater than 4. So it's 5 or greater, means that you'll round that 5 up to a 6. Truncation means that you just chop it off to the right. So 3.14 or 3.15, because again, you're just disregarding that number to the right. All right, so same discussion for this number here and for this number here regarding rounding and truncation. Moving along here. Now we're going to talk about combining two numbers, right? I think that we all, at this point in our academic careers, know how to add, subtract, multiply, and divide. So we're not going to spend a lot of time here. But we're just going to recall the symbology for adding two numbers. Of course, we use this plus sign. Oh, by the way, A and B represent two numbers. A minus B, or subtraction, difference, all mean the same thing. Multiplication, all of these are ways of expressing the fact that you're multiplying A times B. In other words, you're taking the product of A and B. And here are a couple of ways of expressing the fact that you're taking A divided by B, whether you're actually doing the division, writing a ratio, or just writing a fraction. We can call it a fraction. More accurate to call it a quotient or ratio. It's division. So if you were given some sort of operation using words, then we can translate it to math just by going ahead and writing the numbers together with the plus sign and the equals. This says that 2 plus 7 is equal to 9. Or in other words, the sum of 2 and 7 is equal to 9. Or if we want to say that the product of 3 and 5 is 15, well, you can write it like this. So same discussion for difference and quotient. All right, when we talk about evaluating numerical expressions, what we mean is to find the value of some sort of expression. Now, when we say expression, we don't mean equation. An equation is basically a statement that says, you know, some expression is equal to some other expression. Now, we'll talk about equations later in the course, but for now, remember that an expression is just some combination of numbers using the different operations. Now, we're going to talk about order of operations here. And you probably remember some sort of ditty. Please excuse my dear Aunt Sally. Something like that. That basically says something like that you have to deal with the grouping symbols first and exponents you know, multiplication, division, addition, and subtraction. Now, if you've got three numbers and you're going to add two numbers together and multiply as well, so for example, if you have 2 plus 3 times 5, well, what do you do first? You add or do you multiply? And the rule is that, excuse me, is that you multiply first, and then you add. So you do 3 times 15, sorry, 3 times 5 is 15, and then you get 17. Excuse me, and cough a little bit. All right, so if you have 3 plus 4 times 5, that means you'll take 4 times 5 is 20, and 20 plus 3 is 23. Or if you've got 8 times 2 plus 1, that means that you're going to do 16 plus 1 is 17, because you did the multiplication first. Or 2 plus 2 times 2, you do the 2 times 2 first, which is 4, and then 4 plus 2 is 6. Now let's take a look at these. Now you are dealing with grouping symbols, parentheses in particular. And guess what? You're going to do what's in the parentheses first. 5 plus 3 is 8, and then 8 times 4 is 32. Or down here for part B, you got 4 plus 5 is 9, 8 minus 2 is 6, and then 9 times 6 is 54. Okay. So here's the rules for the order of operations. If you have not just one set of parentheses, but multiple sets and even multiple layers or levels, then you'll work with the innermost grouping symbol and work your way from the inside out. And do what's in the grouping symbols first, and then you'll do your multiplications and divisions. And oh, by the way, if you have exponents, do exponents before multiplications and divisions, working from left to right at that level. And then finally, additions and subtractions, moving from left to right. All right, so here's some more examples here. So for part A, we have 8 times 2 plus 3. So of course, you'll do the multiplication 8 times 2 first, and then add 3. You get 19. For part B here, 5 times 3 plus 4 plus 2. Well, you're going to do the 3 plus 4 first, because you take care of the grouping symbol first. 3 plus 4 is 7. Then multiply, because multiplication comes for addition. 5 times 7 is 35, plus 2 is 37. For part C, you can kind of think about this fraction bar as a grouping symbol. So you're going to do the numerator, do the denominator. Now in the denominator, you got multiplication, so you'll do multiplication first. 4 times 7 is 28. Then you could do the summation in the top and summation in the bottom. 2 plus 5 is 7. 2 plus 28 is 30. And then you could leave your answer as this fraction if you want, or you could do division. Now I can tell you right now that 7 divided by 30 is going to result in some sort of decimal, which is fine. If it's a repeating decimal, then you would have to indicate the division. Oh, by the way, I happen to bring my calculator to class with me today. In fact, I've got two calculators. I've got my TI-30, and here's 7 divided by 30, and 2,333, so 0.2333. So I could write this as, oh, actually that's an equal sign, because I'm going to write like this, 0.23 with an overbar. So if you want to indicate that repeating decimal, put an overbar over the digit or digits that are repeating. In this case, it's only the 3 that's repeating, so we've got the overbar just over the 3. Now, if you just wanted to do an approximation, we could just write it as approximately equal to 0.23. Okay? All right, for part D of this problem, now notice in this expression right here, you've got two layers of grouping symbols. So do the innermost grouping symbol first. 6 plus 10 is 16. So there's your 16 there. 16 times 2 is 32. All right, so you did that multiplication before the addition. And then do the addition. 32 plus 4 is 36. And then finally do the last bit of addition to get 38. Okay? So notice that we worked our way from the inside out to evaluate this stuff in the parentheses and then to finally combine it with that other number. Don't worry, you'll have the chance to do some problems on the homework. Now, as it says right here, when you are evaluating these expressions on your calculator, make sure that you're using grouping symbols, parentheses, to include, numerators and denominators, for example, because if you fail to adequately use parentheses, then you will undoubtedly get the wrong answer. Okay, so that's just a warning for all of us. Now, let's take a look at some properties of real numbers. Properties are basically things that hold true all the time. All right, so first of all, we have the reflexive property that says for any real number, it's equal to itself. All right. Symmetric property says that if you have two numbers, A and B, and we say that A is equal to B, that means that B is equal to A. Pretty straightforward, right? So we're talking about the equality sort of relation. Transitive property says that if A is equal to B and B is equal to C, therefore A must be equal to C. And the substitution basically says that if A is equal to B, and so if you have some sort of equation or expression involving the one, then you can substitute the other in place of it. We use that when we're solving equations. So, for example, if you have x plus y is equal to 3, but x minus y is equal to 7 or something, well, you could take one equation and solve for x, and then, so if x really is equal to y plus 7, then you can plug that into the other equation. And now, so you see this x right here, replace that by y plus 7. So you have y plus 7 plus y is equal to 3. And now you can go ahead and solve for y. You have 2y plus 7 is equal to 3. That means that 2y, if you subtract 7 from both sides, 3 minus 7 is a negative 4. And then finally divide both sides by 2. So this principle of substitution comes in handy, especially when you are solving equations. And then finally, if y is equal to negative 2, then x must be equal to, if you plug in negative 2 for y there, that means that x is equal to 5. Okay. So anyway, here's the 4 properties that the equality relation holds for real numbers. So, focusing on commutative property. Now, this is for addition. Now, commutative basically says is that you could do it in either order if you want. You're going to combine two numbers, right, by addition. It doesn't matter what the order is. If you want to do 3 plus 5, for example, you're going to get 8. If you're going to do 5 plus 3, you're going to get 8. So that means 3 plus 5 is equal to 5 plus 3. Or if you want to multiply two numbers, multiplication is also commutative. So if you want to, for example, take 2 times 3, you're going to get 6. If you want to do 3 times 2, you're also going to get 6. So it doesn't really matter what order you multiply any two real numbers. You're going to get the same result. So here's commutative properties for addition and multiplication. Commutative. When we talk about commutative, think about the word commute, as in going back and forth between 2 points, as in between home and work. Associative properties talks about, hey, how do you combine 3 numbers? So, for example, you want to add 3 numbers, 2 plus 3 plus 4. How do you do it? Well, you're going to have to add 2 numbers first, and then add the third one. So which 2 numbers that you want to add together? Well, you could do 3 plus 4 to get 7, and then take 2 plus 7 to get 9. That's fine. Or if you want to do the first 2 numbers, 2 plus 3, you get 5, and then add 4 to get 9. It doesn't matter. Associative property says if you got 3 numbers, you want to add them together, you can add together any 2 first, and then add the other one next. So associative property basically says that. And here's the same example for multiplication. You want to multiply 3 numbers together, you can combine 2 numbers first and then multiply the third one. It doesn't matter which 2 that you start off with. So here's the associative properties for addition and multiplication of real numbers. Okay. Distributive property basically says if you're going to combine 3 numbers by adding 2 numbers and multiplying by a third number, well, you can add the 2 numbers first and then multiply by the third number, or you can multiply first and then add the results, either from the left or from the right for the distributive property. So, for example, if you have 2 times quantity x plus 3, well, you could write that as 2 times x plus 2 times 3. In other words, you're distributing this 2 to the x and the 3. You could also do the backwards motion here. If you have 3x plus 5x, well, guess what? X is common to both of those terms, so you could actually kind of pull out the x and write that as 3 plus 5 times x. And then 3 plus 5 is 8x. So this actually tells us how to add like terms. Or if you've got x plus 2 times x plus 3, you could distribute the x plus 3, this guy right here, to the 2 and also to the x, like you see that we've done there. And then use the distributive property yet again to get that and to get that. Right? We use the distributive property on this one to get that right here, and use the distributive property there to get this. And then combine like terms. Okay? So when you FOIL out the product of 2 binomials, you're actually doing a double application of the distributive property. Let's now talk about the identity. 0 is the additive identity for a real number system, and 1 is the multiplicative identity for our real number system. Now, 0 is the number that when you add it to any other number, you get the same number. So 0 plus 4, for example, is 4. 1 is that number that when you multiply it to any other number, you get the same number. So 3 times 1 is 3. 1 times 3 is 3. Doesn't change the number that you multiply by. So here's the identity properties. 0 is the additive identity. 1 is the multiplicative identity. Moving along here. Now, the additive inverse is nothing more than just the negative of a number. So the additive identity of, say, 6 is going to be negative 6. It's going to be that number that when you add a number together with its inverse, you're going to get 0. You're going to get the identity. And the additive inverse of negative 8 is going to be positive 8 because negative 8 plus 8 is 0. Okay. The additive inverse is nothing more than just the negative of a number. Now, the multiplicative inverse of a number is nothing more than the reciprocal. Reciprocal. You flip the number upside down. It's that number that when you multiply a number times its multiplicative inverse, you always get 1. 1 is the multiplicative identity. So the reciprocal of 6 is 1/6, because when you take 6 times 1/6, you get 1. Negative 3 and negative 1/3, they are inverses of each other because their product is equal to 1, right? The reciprocal or the multiplicative inverse of 2/3 is 3/2. Because when you multiply them together, you get 1. All right, moving along here. Now, when we talk about subtraction, we're, in other words, saying we're going to take the difference of two numbers. One way that you can think about saying A minus B is saying A plus the negative of B. Okay? If you wanted to do division, some number A divided by some other number B, we could say we're taking the quotient of A and B. In other words, we're taking A divided by B. We could write it as this fraction right here. But we could also say that this is A times the reciprocal of B, or the ratio of A to B, or A times the multiplicative inverse of B, provided that, of course, that B is not 0, because we don't know how to divide by 0. So, for example, 8 minus 5 is the same thing as 8 plus negative 5, which is 3, of course. Or 4 minus 9 is the same thing as 4 plus negative 9, which is negative 5. You could think about 5/8 as 5 times 1/8. Or in other words, 5 times the reciprocal of 8. 5 times the multiplicative inverse of 8. By the way, when you take any number times 0, you always get 0. Hopefully we all remember that. And if you take 0 divided by any non-zero number, you get 0. 0 divided by 2 is 0. 0 divided by any number is 0, provided that you're not dividing by 0. Any number divided by itself is 1. Now, when we take a number times the negative of some other number, then you could talk about saying, well, then that's going to be the negative of the product of those two numbers. And these other two equations all are simply saying, how to combine two numbers where you have one number together with the negative of another number. Now, this third one says that, you can think about the two negatives canceling here. You have the negative of A times the negative of B, whatever A and B are, but you're the negative of both of those. The two negatives will cancel. So negative 3 times negative 4 will be positive 12, for example. The negative of a number is going to be just the number itself. So the negative of negative 4 is 4. When you have a quotient of two numbers and one of those numbers is negative, then you could pull that negative out front, like you see here. If you have a negative number divided by a negative number, the two negatives will cancel, leaving you just with the quotient of those two numbers. So, for example, if you have 2 times negative 3, that's just going to be negative 6, right? Negative 3 times negative 5, the negatives cancel, leaving you just with 15. 3 times 5 is 15. If you have 3 over negative 2, you could write that as negative 3/2. You have negative 4 over negative 9, the negatives cancel, leaving you just with 4/9. You can kind of think about x over negative 2 as negative 1/2 times x. Now, we're going to talk a little bit about cancellation. Now, if you have this sort of equation right here, and you've got a common factor on both sides, like c in this case, then you can cancel out the c, provided that c is not 0. Because you can't divide by 0. If you have the quotient of two numbers, as in a fraction like this, and the numerator and denominator have the same factor, then you can cancel that factor, leaving you with a over b in this case. So, for example, if you have 2x equals 6, you could think about 6 as 2 times 3, and then you can cancel the 2's. So that means that x is equal to 3. So you see there. Or if you have 18 over 12, you can think about 18 as 3 times 6, think about 12 as 2 times 6, cancel the 6's. That leaves you with 3/2. Now, I know that we're going through all this in a real hurry, and I certainly hope, though, that this is all review for you, and that this time well spent by you. Now, listen, if you've got the product of two numbers and the result is 0, it has to be that at least one of those two numbers is 0. It could be that both is 0. So, for example, if I say that 2 times x is 0, that means that either 2 is 0 or x is 0. Well, guess what, folks? I know that 2 is not equal to 0. So if 2 is not equal to 0, then what does that say about x? If 2x is equal to 0, that must mean that x is equal to 0. Also, if I have x plus 3 times x minus 2 is equal to 0, then that means that either x plus 3 is equal to 0 or x minus 2 is equal to 0. So you set each of those factors equal to 0 and then solve for x. And if x plus 3 is equal to 0, that means x is equal to negative 3. And if x minus 2 is equal to 0, that means that x is equal to 2. So you have two possible solutions in this case. So we use the zero product property a lot in this class. So make sure that you are aware of it. A quick refresher on adding two fractions. In order for you to add two fractions, you need to get a common denominator. Oftentimes you get a common denominator by finding the least common multiple of the denominators. Greatest common or least common divisor. Lowest common denominator, I mean. LCD, lowest common denominator. In other words, the LCM of the two denominators. Now, that's for adding and subtracting fractions. You need a common denominator. If you're multiplying two fractions together, you just multiply the numerators, multiply the denominators. If you have one fraction divided by another fraction, then you could take that top fraction times the reciprocal of that bottom fraction, like you see here. You just invert and multiply. So for example, if you wanted to take 2/3 plus 5/2, well, look, the least common multiple of the denominators, 2 and 3, is 6. So that means that you can multiply the 2/3 right here by 2 over 2, and multiply the 5/2 by 3 over 3. So you have a common denominator of 6. And now the numerators are 4 and 15. 4 plus 15 is 19, so 19/6 will be the result of adding these two fractions. If you wanted to do the subtraction here, 3/5 minus 2/3, find the least common multiple of the denominators, 3 and 5, well, that will be 15. So multiply the first fraction by, 3/3, and that second fraction by 5/5. Add the numerators, and you get negative 1/15. Or if you need to multiply these two fractions together, go ahead and multiply the numerators, multiply the denominators, factor that numerator, factor the denominator, cancel any common factors that you see here, and simplify. The result is 10. Or if you have 3/5 divided by 7/9, take that as 3/5 times 9/7. And then multiply the numerators. 3 times 9 is 27. 5 times 7 is 35 for the denominators. Cancel any common factors, which there aren't any in this case. So there's your final answer. Now, it's one thing to say that the least common multiple of 3 and 5 is 15, but what about, multiple digit numbers? You want to find the least common multiple of, say, 12 and 15. Now, one simple way of finding the least common multiple of two numbers is to go through and start writing multiples of each number. Like, so for example, 15, go ahead and start writing, multiples of 15. There's 15, 2 times 15 is 30. Add another 15, you get 45. Add another 15, you get 60, and so forth. And then do the same thing with 12. Go ahead and write multiples of 12. 12, 24, 36, 48, and so forth. And then locate that first number that's the multiple of both the 12 and the 15. 60 in this case. 120 is also a common multiple, but the smallest common multiple is 60. So that's why 60 is the LCM of 12 and 15. Now, I'm going to show you a different way of finding the LCM. So take a look at 12, do the prime factorization of 12. 2 times 2 times 3. Do the prime factorization of 15, that's 3 times 5. Now, the least common multiple of these two numbers will be the one that contains 2 2's, a 3, 3 is common to both, and also a 5. And now 2 times 2 is 4, 4 times 3 is 12, 12 times 5 is 60. Okay, so there's a more sophisticated way of finding the LCM of two numbers by look at the prime factorization of the numbers, and then LCM will be that number that has the most count, the highest count of each of the prime factors. Okay? So whatever method works best for you. So anyway, if you wanted to add 8/15 plus 5/12, well, the least common multiple is 60. 60 is 15 times 4, so you'd multiply this first fraction by 4 fourths, and this 12 here is 60 divided by 5, so you multiply top and bottom by 5 like that. So then that's what guides you to go ahead and get that common denominator, add those numerators, and simplify as needed. Okay. Now 57 has a common multiple, or a common factor of 3, I should say. 57 divided by 3 is 19. So you can cancel a factor of 3 between the top and bottom. So 19/20 would be your answer. So that's going to wrap up the very first section of the review chapter. Now, I'm going to go ahead and post this video, but I'm also going to work on posting a bunch of PowerPoints, not all at the same time, but over the next several days I'll eventually get all the PowerPoints loaded up on Blackboard so you can follow along in the future. Okay, so that's going to be it for today, and we'll see you next time, okay?